So in today's class, we will try to understand what is the physical significance of wave function psi and the physical significance of square of the wave function psi square. Okay, or sometimes we take product of psi star into psi. Okay, so we'll try to understand the physical meaning of these two. I have written here the Schrodinger wave equation in different forms. The first equation is nothing but the one-dimensional Schrodinger wave equation representing a particle having wave nature moving along x-axis, whereas the second equation is the general time independent Schrodinger wave equation for a particle and the wave associated with it traveling in three-dimensional space, whereas this is the well-known form of writing the Schrodinger wave equation. H of psi is equal to E into psi. When we apply the Schrodinger wave equation for a particular system containing one particle or n number of particles, so when we apply the Schrodinger wave equation and solve it, we get two important information upon solving the Schrodinger wave equation. What are those two information? One is we obtain the eigen function, that is the wave function psi, and the other is the corresponding energy E, which is the eigen value. Okay, so when we solve a Schrodinger wave equation, remember this, we obtain the eigen function, which is the wave function psi, and the eigen value, that is the energy E. Here the wave function psi of x, which represents the function for a one-dimensional system, or psi of x comma y comma z, which is a wave function for a particle in three dimension. It represents the amplitude of the wave that is associated with the particle at that position x or xyz. Okay, I repeat, psi of x or psi of x comma y comma z just represents the amplitude of the wave associated with the particle like electron at the position x in one dimension or xyz in three dimension. Okay, this we have already discussed when we solved or when we derived the Schrodinger wave equation. Psi of x is called as the wave function representing the amplitude, and it has no other physical significance. Okay, it only represents the amplitude, and by knowing this wave function psi, we do not get any critical information about the system. And remember, when you solve a differential equation of this kind, the resulting mathematical function, that is eigen function or wave function, may be a real function or it may be a complex function. What do you mean by a complex function? Complex functions are those functions which contain the imaginary number I, which is equal to square root of minus 1. So when a Schrodinger wave equation is solved, the resulting wave function, that is eigen function, may be a real function or it may be a complex function, and these functions represent the amplitude of the wave associated with the particle, and this psi of x or the amplitude has no physical significance. It does not tell us anything about the system, but what is very important is the square of that wave function, the square of the amplitude or the square of the wave function. So let us now try to understand what is the physical significance of square of the wave function psi square or psi star into psi. Okay, so we calculate psi square, okay, when the wave function psi is a real function, and if the wave function psi is a complex function, we replace psi square by psi star into psi, where what is psi star? I already told you in the last class. Psi star is the complex conjugate function of psi. Okay, psi star is a complex conjugate of psi. How do you calculate the complex conjugate of a function psi? If you have a function, say for example e to the power ix, its complex conjugate is e to the power minus ix. So what we are doing is we are just changing the sign of the imaginary component of the function. Okay, so for example, if the function is cos x plus I into sin x, its complex conjugate is cos x minus I into sin x. So we just change the sign of the imaginary part of the complex function. So we calculate psi square if the function is a real function, and we calculate psi star into psi if the wave function or the eigen function is a complex function. From our previous knowledge about a wave, okay, we know that square of the amplitude of any wave, whether it is a light wave, whether it is a sound wave, or whether it is a water wave, the square of the amplitude of a wave at a particular point, it gives the intensity of the wave at that point. So intensity of the wave is directly proportional to square of the amplitude. It means greater the amplitude of the wave at a particular point, greater is the intensity of the wave. Lesser the amplitude of the wave at a particular position, lesser is the intensity. So intensity is directly proportional to amplitude square. So the same analogy can be applied to this particle wave also. So what is psi square or psi star into psi representing? They represent the intensity of the electron or the particle wave. To be more uh, particular, this, okay, it represents the probability, okay, it represents the probability of finding the particle at a particular point x or a particular point xyz, okay, in 3 dimension. So I repeat, what is the importance or what is the meaning of square of a wave function psi square? Psi square is nothing but the probability of finding the particle at that particular position x in 1 dimension, or the particular position x comma y comma z in 3 dimension. Okay, now two things we have to consider here. Why for a real function we consider psi square, and for a complex function we consider psi star into psi? Why? Because this psi square or psi star into psi are representing probabilities, and probability is always a real number. Probability cannot be a complex number. If psi is a real function, psi square will always be a real number. But if psi is a complex function, then psi square may also lead to a complex number, and probability cannot be a complex number, it should always be a real number. So instead of using psi square, we use psi star into psi. Okay, because from our previous mathematical classes, from our PU classes, we have studied that psi star into psi is always a real number. So if I have a complex number z and its complex conjugate z star, z into z star is always a real number. So if I apply the same rule here, if psi is a complex function, then psi into psi star will always lead to a real number. So if the function is a real function, we use psi square to calculate the probability. If it is a complex function, we use psi star into psi to calculate the probability. So I have given a one-dimensional example here. So in the, along the, this is the x-axis which represents the position of the particle. So the particle, okay, for example electron will be moving anywhere along x-axis, and along y-axis I have plotted wave function psi of x. So you can see the wave nature of the electron, and the height of this wave is different at different positions. So as the values of x changes, the height of the wave, that is the value of wave function psi of x, also changes. So let me take one particular point x, okay, where the particular, okay, x, where the wave function has value psi of x. So I am taking one particular position x of the particle where the wave function has value psi of x. Now if I ask myself the question, okay, I will select a small interval along x-axis. This is x, this is position x plus dx, where dx is a very small number. So the question is, what is the probability that that particle or the electron is between x and x plus dx? Okay, I repeat, what is the probability of finding the particle between x and x plus dx? The answer to this is, the probability of finding the particle between x and x plus dx is calculated as psi x square into dx, or you can simply write it as psi square into dx. Okay, if psi is a real function. If this psi is a complex function, we use psi star of x into psi of x into dx. So this expression is used to calculate the probability of finding the particle between the region x and x plus dx, a very small length of very small region of length dx. Suppose if the electron is traveling in 3 dimension, that is x-axis, y-axis as well as z-axis, then how do you calculate the probability of the particle? So suppose if the particle is at a position xyz, which I have shown here, this is the position xyz. So what is the probability of finding this particle within the region dx along x-axis, within the region dy along y-axis, and within the region dz along the z-axis? So I have drawn a small imaginary cube, okay, a cube in the space. The volume of this cube is dx into dy into dz. Okay, the volume of this very small cube is dx into dy into dz. So the probability of finding the particle within this cube having volume dx into dy into dz is given by psi square of x comma y comma z, dx into dy into dz if it is a real function, or we use psi star into psi into dx into dy into dz. This dx into dy into dz, in the last class I have already told you, it is called as the volume element d tau. So d tau is nothing but dx into dy into dz in 3 dimension. If we are working with a 1 dimensional problem, d tau is equal to dx, the unit, a small length. If it is a 2 dimension, then d tau is equal to dx into dy, a very small area. If it is 3 dimension, then d tau is equal to dx into dy into dz, a small volume. So the probability of finding the particle in 1 dimension is psi square into dx, or psi star into psi into dx. Probability of finding the particle in 3 dimension is psi square into dx into dy into dz if it is a real function, or psi star into psi into dx into dy into dz for a complex function. Now the more important point that we have to figure out here is why this word probability appears here. Okay, why this intensity is considered as probability of finding the particle. Okay, we all know that the exact position and the momentum of a particle like electron or atom or molecule cannot be determined accurately and simultaneously. This is nothing but Heisenberg's uncertainty principle. According to Heisenberg's uncertainty principle, the position and the momentum of a subatomic particle like electron cannot be determined accurately and simultaneously. So we cannot exactly pinpoint where the electron is. I cannot say the electron is at a position x comma y comma z in 3 dimension, or I cannot say the electron is at a particular position x, particular point x in 1 dimension. What I can maximum say is what is the probability that the electron is present at this particular position x, or what is the probability that the electron is present at a particular position xyz. So because of Heisenberg's uncertainty principle, because of that principle, we cannot exactly pinpoint where the electron is. What is the exact position or the location of electron, we cannot say. We only speak in terms of probability. ಓಕೆ, ಯಾಕಂದರೆ ನಮಗೆ ಎಕ್ಸಾಕ್ಟ್ಲಿ ಏನಾಗ್ತದೆ ಅಂತ ಗೊತ್ತಿಲ್ಲದವಾಗ ವಿ ಆಲ್ವೇಸ್ ಸ್ಪೀಕ್ ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ಪ್ರೊಬ್ಯಾಬಿಲಿಟಿ. ಇಲ್ಲಿ ಪೊಸಿಷನ್ ಆಫ್ ದಿ ಎಲೆಕ್ಟ್ರಾನ್ ಅನ್ನು ಕರೆಕ್ಟಾಗಿ ನಮಗೆ ಹೇಳಿಕ್ಕೆ ಆಗ್ತಾ ಇಲ್ಲದ್ರಿಂದ ವಿ ಹ್ಯಾವ್ ಟು ಸ್ಪೀಕ್ ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ probability of finding the electron. And how to calculate the probability? I have already told you, psi square into dx if it is a real function, or psi star into psi into dx if it is a complex function. So this is the physical meaning of psi square or psi into psi star. Okay, now we will try to understand, okay, the exact meaning of a well-behaved function. Mathematically we had defined what is a well-behaved function in our previous class. Okay, any wave function or an eigenfunction that we use in quantum mechanics should be a well-behaved function. And how do you mathematically define a well-behaved function? A well-behaved function should be a finite function, it should be continuous function, it should be single valued, and it should also be a normalized function. Now let us try to understand why a well-behaved function should have these features or these characteristics. Why a well-behaved function should be finite, why it should be continuous. What happens if the well-behaved function is infinite? Why can't we use a well-behaved function which is an infinite function? Or why can't I use a well-behaved function which is not a single valued? Why we should impose these conditions for a well-behaved function? The answer is very simple. Okay, if you remember this point, then it is very easy to answer this question. Okay, why the wave function should be finite, continuous, single valued and normalized is because though the wave function psi does not have any physical meaning, but its square, okay, psi square has a very important physical meaning. And what is the significance of psi square? It represents the probability of finding the electron. Psi square or psi star into psi represents the probability of finding the electron. And probability is always a number lying between 0 and 1. Probability cannot be less than 0, it cannot be greater than 1. The least value of probability is 0, lowest value is 0, and the highest value of probability is 1. So probability always lies between 0 and 1 value. So it is always a finite value. Probability is always finite. So if a wave function becomes infinite at a particular value of x, okay, if psi of x becomes infinity at a particular value of x, okay, at a particular value of x, it means it is not a finite function. It is not a finite function. So what does it mean? If I take the square of this, that is psi square of x is also equal to infinity. What does it mean? It means that the probability of finding the particle at position x is infinity. And I already told you probability cannot be infinite. It is always a finite value between 0 and 1. That is the reason why a well-behaved function should be a finite function. Second, why it should be a continuous function. I already explained to you the nature of a continuous function. Continuous function, okay, is this a very smooth curve or a very smooth function. ಏನಂದ್ರೆ ಅರ್ಥ? Suppose if I vary the value of x, that is the position of the particle, psi of x should change gradually. Or if I change the value of x, psi square of x should also change gradually. What does it mean is, if I have x here, okay, this is y, that is nothing but psi of x. Suppose if at this value x1, okay, psi of x is very less, it means psi square is also very less. Probability of finding the electron is very less. And at a point very close to x1, that will take it as x2. They are extremely close to each other. If the value of psi of x is very high, so this is not a continuous function, because for a very small change in the value of x from x1 to x2, there is a abrupt change in the value of psi of x. So this is not a nature of a continuous function. So what will happen is, if I take this square, it represents the probability. So at x1, the probability of finding the electron is very less, whereas in its neighboring point, which is very close to x1, the probability of finding the electron is very high. And this cannot happen, because when the electron moves from one position to another position, the probability of finding the electron should change gradually. So here, what does it say? This position, okay, has least favor for occupying the electron, whereas this position, which is very close to x1, has a very high favor for the electron, which is not possible, because when the electron moves from one point to another point, it touches all the point. So the probability of the electron cannot jump all of a sudden between two very close points. So that is the reason the function should vary smoothly, or it should be a continuous function. The third point is, it should be single valued. Suppose if psi of x is equal to 0.5 at x is equal to 1, and psi of x is equal to 0.6 at x is equal to 1. So this is not a single valued function, because for the same value of x, the function has two different values, 0.5 and 0.6. This cannot happen. The function should have only single value. Okay, why it should be a single value? Because if it has two different values, now let me take the square. What is psi square of x for this particular point? It is 0.25. What is the psi square of x for the second value? It is 0.36. So what does it indicate? At the same value of x, that is at the same position for the electron, one probability predicted value is 0.25, the other value is predicting a probability of 0.36. So for the same position we are having two different probabilities, which is not possible because there is only one probability value for a particular position x. So that is the need for a single valued function, okay, in quantum mechanics. So physically we have we try to explain why a well-behaved function should be finite, continuous and single valued. The final desirable property of a well-behaved function is it should be a normalized function. So what do you mean by a normalized function? Now psi square, okay, psi square, or okay, first I will write normalized function, or it is called as normalization condition. So when we solve a Schrodinger wave equation, we get an eigenfunction which is well behaved, that is it will be finite, single valued and continuous, but it may not be normalized. But we can make it a normalized function by applying this condition called as normalization condition. What is this normalization condition and why? What is the necessity of applying this normalization condition? Now we already know that psi square or psi into psi star, okay, if it is one dimension into dx, this is psi into psi star into dx, represents the probability of finding the particle along x-axis in a very small region dx. Suppose if we assume that, okay, this is the x-axis, this is the origin, this is minus infinity to plus infinity. So suppose the electron is given the freedom to travel anywhere along x-axis from minus infinity to plus infinity. Now what is the meaning of this term psi square into dx or psi into psi star into dx? Suppose if I select a point x here and I select another point x plus dx which is very close to x. So the length of this interval or region is dx. So what is psi square into dx? Psi square into dx represents the probability of finding the particle or the electron in this small region dx. Now if I ask the question, what is the total probability, okay, of finding the particle between minus infinity to plus infinity? How will you find out the total probability? You can find the total probability by adding this small probability, okay. I already know what is psi square into dx. What is psi square into dx? It is the probability of finding the particle at this small region dx. ಅದೇ ರೀತಿ ಪಕ್ಕದಲ್ಲಿ ಮತ್ತೊಂದು ರೀಜನ್ ತಗೊಳ್ತೇನೆ dx, ಅಲ್ಲಿ ಕೂಡ probability ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೇನೆ, that will be psi square into dx. ಅದೇ ರೀತಿ ಇಲ್ಲಿ ಒಂದು ಸ್ಮಾಲ್ ರೀಜನ್ ತಗೊಳ್ತೇನೆ dx, I will calculate the probability psi square into dx. So if I add all such small probabilities, that would give the total probability of finding the electron from minus infinity to plus infinity. So the total probability of finding the particle should be psi square of x into dx. Adding them, how do you add in mathematics? That is by integration from minus infinity to plus infinity. So you are adding the small probabilities in the region of length dx. So anta small probabilities and add madidre, that would give the total probability. And how do you add the small probabilities? The addition is done by using integration. So the total probability is minus infinity to plus infinity psi square into x into dx if psi is a real function, or if it is a complex function, the total probability will be integration minus infinity to plus infinity psi star of x into psi of x into dx. Now what is the total probability of finding the electron? The electron can be anywhere between minus infinity to plus infinity, but the total probability that the electron is somewhere between minus infinity to plus infinity should be equal to 1, right? ಯಾಕಂದ್ರೆ electron ಈ particular point ಅಲ್ಲಿ ಇದೆಯೇ ಇಲ್ವಾ ಅಂತ ಕೇಳಿದ್ರೆ probability may be very less. What is the probability of finding the electron here? Okay, the probability may be very less because electron ಇದು ಒಂದೇ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಇರಲ್ಲ, it will be continuously moving. But ಈಗ ನಾನು ಏನು ಕ್ವಶನ್ ಕೇಳ್ತೇನೆ, electron is somewhere between minus infinity to plus infinity. What is the probability? The total probability should be equal to 1. ಯಾಕಂದ್ರೆ at any instant of time the electron should be somewhere between minus infinity to plus infinity. So the total probability will be equal to the maximum value, that is equal to 1. So this integration is nothing but equal to 1. So minus infinity to plus infinity psi square of x into dx, or integration minus infinity to plus infinity psi star into psi into dx should be equal to 1. The total probability of finding the particle anywhere between minus infinity to plus infinity should be equal to 1, and this condition is nothing but called as the normalization condition. So this condition is nothing but the normalization condition. So what is normalization condition? The total probability of finding the particle in the space somewhere between minus infinity to plus infinity, that should be equal to 1. And when we solve a Schrodinger wave equation, ನಮಗೆ ಏನು ವೇವ್ ಫಂಕ್ಷನ್ ಸಿಗ್ತದೆ ಅದು ನಾರ್ಮಲೈಸ್ಡ್ ಆಗಿರಲೂಬಹುದು ಆಗದೇನೂ ಇರಬಹುದು. ಇಫ್ ಇಟ್ ಇಸ್ ನಾಟ್ ನಾರ್ಮಲೈಸ್ಡ್, ವಿ ಹ್ಯಾವ್ ಟು ಮೇಕ್ ಇಟ್ ನಾರ್ಮಲೈಸ್ಡ್. ವೈ? ಬಿಕಾಸ್ that wave function should predict the total probability of the finding the particle in the entire space equal to 1. So if the function is not normalized, we have to make it normalized by applying this normalization condition. So this is corresponding to one-dimensional problem. Suppose if we are dealing with a three-dimensional problem, how will you write the normalization condition? In three dimension, the normalization condition is integration minus infinity to plus infinity psi of x comma y comma z square into dx into dy into dz is equal to 1. Actually this integration is triple integration with respect to x axis, y axis and z axis. Okay, so the total probability is equal to 1 if this is a real function. If it is a complex function, it is integration minus infinity to plus infinity psi star of x comma y comma z into psi of x comma y comma z into dx into dy into dz is equal to 1. This is applicable if the function is a complex function. So this is the normalization condition in 3 dimension. This is the normalization condition in 1 dimension. This we have to use if the function is a real function, and this condition will be used if the function is a complex function. So this is about the physical significance of wave function psi, the square of the wave function psi square, and the normalization condition. In the next class we will apply the Schrodinger wave equation to a very important problem, that is particle in a one-dimensional box.